Hi kids, it's Mrs. Fravel. How are you? All right, me too. Hey, today we're going to talk about water. We're talking about the chemistry of life, chemistry in biology, and water is pretty much the most important chemical to life. And here's why. Water, let's talk about its structure a little bit. Water is made up of two different atoms, two different types of atoms. It's a molecule made of two hydrogen atoms and one oxygen atom, and those are together, stuck together through covalent bonding, which means that the hydrogen and oxygen share an electron. So there are, of course, just quick review of how atoms are built. Inside of every atom, there are protons that are positively charged and neutrons that are neutrally charged. And those two things are in the nucleus of an atom. They give it its mass, its density, its number. And then electrons orbit the outside of atoms, and they have a negative charge. Positives and negatives are attracted to each other. So those electrons orbit in this crazy cloud, however many of them, they usually will match the number of protons. However, when we get two different kinds of atoms that are associated with each other, there might be one atom, like an oxygen atom, that has more room in its electron cloud for more electrons. So it's going to attract those electrons, and they will share an electron between the hydrogen and the oxygen. Okay, so there are in hydrogen atoms, they have one electron. They then start to share that with the oxygen, and that bonds them together into a water molecule. Okay? What that also does is create a state in a water molecule that makes it polar. Okay, get out of the way somewhere. Okay. Water molecules are what we call polar because as those electrons are shared, they are pulled a little more strongly toward the oxygen end. The oxygen atom attracts more than its fair share of the electrons. So that creates an unequal charge in the molecule. So we say oxygen is more negative, hydrogen is more positive. Okay? You should draw you should draw a water molecule. If you're taking your notes digitally, find a water molecule and insert it in your notes, but make sure that you can recognize there are two positive hydrogens at one end of each water molecule and one big electron-hogging oxygen that is negative at the other end. Okay? Now, this is what causes water to be called a polar molecule. However, when you get a mass of water, the water doesn't have a charge. It's actually neutrally charged itself. It's just each individual molecule has that slight polarity because in the sum total of all of the molecules in a body of water, a drop of water, a whatever of water, there is an equal number of electrons and protons. So we say that water is neutral, but each molecule is slightly polar. Okay. How does water stay together? So besides those covalent bonds, there's another kind of bond that happens in hydrogen called hydrogen bonding. So each hydrogen, little white guys on this animation, these are covalently bonded to their own oxygen. However, they are also positive. That positive charge, they are attracted to neighboring oxygen atoms in other water molecules. So they get this pull toward them, and it isn't very strong. Okay, it's a weak bond and it ends up bonding 5 water molecules together in this hydrogen bonding pattern. It's a weak bond, but when you get bazillions of them across a piece of water, that creates a strong flowing force. And those bonds are easily broken. They break apart, they reform. That's what gives water its special qualities. And we're going to talk about each of those. On your notes, you should summarize what hydrogen bonding is in your own words. Okay, you can pause me anytime you need to. Okay. So what are the special qualities of water, special properties of water? Here we go. There are 5 of them. I'm going to go through each one of these individually, but you need to make sure that you know just the words of them. So write them down and then we'll go through them in more detail. Properties of water are cohesion, adhesion, high specific heat, universal solvent, and it is less dense as a solid. And all of those properties are the result of those hydrogen bonds and water's polarity as well. Okay, so let's take these one at a time. Let's talk about cohesion. So the word part co means together, okay? Hesion means to stick, it kind of. So again, you can remember this by taking your little hands and going cohesion, cohesion, cohesion. Cohesion is attraction between particles of the same substance. And so water is attracted to itself. Those hydrogen bonds, again, a hydrogen is attracted to all of the oxygens around it, at least in 5 molecules. And so we get the water's tendency to stick to itself. This results in a couple of different things, including surface tension, which is the strength of the water at its surface, at its interface with the atmosphere. Okay, so surface tension, it's kind of like it's not really a film, but it's at the interface between water and the atmosphere. It tends to be a little stronger. Okay, so surface tension is what allows, if you've ever seen a water bug walk on top of water, that insect is spreading out its weight on its legs enough to displace and push back against the surface of the water on that surface tension. So it uses the surface tension. You may have some experience with surface tension as well. If you've ever done a belly flop into a swimming pool or a lake, that belly flop, when you spread out your weight, you smack off the surface of the water because of the water tension. It's kind of pushing back on you. Okay? It also causes what we see in waves, ripples, curls on waves. Okay, that's all because of cohesion. Water's sticking to itself. This is important in living bodies because it helps plants take up a significant quantity of water all at once. We'll talk about the other property that helps plants take up water. But when they do, because water sticks to itself, they get a significant amount all at once without having to put in a lot more effort into ensuring that they get enough water in their cells. Also, this cohesion, the water stays together. It allows cells to stay plump, have good turgidity. Yes. Okay, so it looks like cohesion is what helps water form droplets, those crazy bugs walking on the water. And then things also can float on water. If something is less dense than water, it will float on top, and surface tension helps keep it up there. Okay. All right. Whew. Fravel's having a hard time talking this morning. I'm trying to get this done quickly because class is going to start. So here we go. Adhesion. So the opposite of co together is ad, which is away. So adhesion is things sticking to other things. Okay, so put your hands up, put your palms out. Adhesion. Cohesion. Adhesion. So make sure you know the difference between those two. Adhesion is water being attracted to other things. Water will make hydrogen bonds with other surfaces depending on the surface. And this is kind of what being wet means. Like, you don't really think about why does something get wet? It's because water sticks to it on a molecular level. Okay, this results in several different phenomena in the natural world and in living bodies. It causes capillary action, which is the other part of helping plants make sure they get enough water. So these hydrogen bonds will form inside of the vascular structures in plants, the xylem and the phloem, the xylem specifically. The water molecules will stick to the inside structures of the plant's tubes and then start to climb itself. So adhesion and cohesion work together in capillary action to stick to the inside of the tube and then climb up it. You guys saw this in the lab that you did last week when you stuck the little straw into the water. And again, you can see if you stick a thin enough tube into water, if you look closely, you can see the little meniscus, and the surface of the water inside of the straw will be curved. That's the hydrogen bonds climbing up the sides of that tube. So water, due to adhesion, gets stuff wet. We see droplets on plants. We see, of course, beautiful things like spider webs with dewy droplets shimmering in the sun. And then you also get big stinky wet dogs. That's why things are wet, okay? In living bodies, this adhesive effect, when the hydrogen bonding occurs in a cell between the cell's internal and external environments and the cell membrane, which we'll talk about in a later unit, the water's hydrogen bonding with that cell membrane's molecules keeps the cell membrane oriented properly. Okay. All right, next property is high specific heat. Water does not like to change temperature. Those hydrogen bonds absorb a lot of energy. The definition of high specific heat or specific heat is how much energy it takes to raise something's temperature 1 gram by 1 degree centigrade. With water, it takes a lot of energy. It resists temperature change, both getting warmer and getting cooler. Okay? It absorbs a lot of heat and it doesn't change its own temperature. In bodies, this is what helps cells maintain and help bodies maintain a regular temperature. If your body's full of water, it's not going to heat up or get too cold too quickly. The body can do metabolic things or behavioral things to make sure and maintain that temperature before the water cools down too much in the cells or heats up too much in the cells, which can cause some protein deformation and denaturization, which interrupts homeostasis. All right. Also, water doesn't like to evaporate. High heat of vaporization is going from a liquid to a gas, and water doesn't like to do that. The hydrogen bonds, individually, of course, they're not real strong, but together they are, so they don't break apart very easily. So water doesn't evaporate as quickly as other liquids. It takes a lot of energy to evaporate water into a gas. And in bodies, again, this helps with cooling and maintaining a good temperature, because as it evaporates, because it uses so much energy to evaporate, it takes away the heat of it. So when you sweat, that's why you sweat. The water on your skin is going to evaporate and take away a lot of the heat to maintain your internal body temperature. Okay. All right, water is also, man, I should just get out of the way. Water is also an excellent universal solvent. What does that mean? Being a solvent means that a liquid can dissolve solids in it. Essentially, it's taking a solid and pulling it apart into its constituent molecules, so the molecules dissolve in water really easily. Especially ions, which are molecules or substances that have a slight charge to them, like salts. Those are attracted to the polarity of the water molecules and are very quickly pulled apart into a solution. Solutes are the dissolved chemicals in the water, and these are a lot of organic compounds. Okay, and so where the importance in a body is that water can carry nutrients and salts with it, organic molecules that bodies need in order to do their metabolism and build their structure. So water pulls nutrients into cells. And of course, in a solution, water, oh boy, howdy. I don't know. Not quite sure why Fravel's not yet awake, but I'm going to try this again. So solutions are made up of a solvent, which is the liquid, in this case water, and the solute, which is the dissolved solid. Okay, so solution is solvent and solute. Water, again, this is a saltwater solution. Sodium chloride is salt. Those are ions that are pulled apart by water, and that's why when you put salt in water and then you stir it, the salt disappears. It dissolves, right? Makes a solution. And I think this is the last property of water. Water is less dense as a solid, which is weird. Usually when a liquid cools and solidifies, it is more dense, meaning if you took a chunk of it and put it into its own liquid, it would sink. But water doesn't do that, right? We see water as water ice. We watch it floating. And that's because of the way the hydrogen bonds orient to each other. When water cools down, those flowing hydrogen bonds slow and water starts to condense, starts to kind of condense and get a little more dense. But then right at the point of freezing, then those hydrogen bonds lock into a specific angle, and we get these spaces between the molecules that cause the water to be less dense as a solid. So liquid water, we see the molecules are just kind of moving around each other, next to each other, but then at the instant of freezing, that solid ice creates spaces between the molecules that spreads them out, that lowers the density. All right, again, throughout this, I've kind of been trying to mention how all of these properties are important in living bodies. So essentially, water is necessary for homeostasis. And homeostasis is the ability to maintain a steady internal state, no matter what's going on around a body or a cell in the environment. And again, water does this because it resists temperature change. It carries nutrients that are dissolved and absorbed more easily because they're riding in water. And also it, as ice in nature, it helps maintain the temperature of the planet, and it can also insulate and protect life in a body of water, because when that ice floats on the top of a lake, it's going to insulate and keep the rest of the lake liquid underneath it, so that organisms can live in that water throughout the cold. Whew. All right, one more thing. Okay, let's talk about pH. pH is a measure of hydrogen ions in a solution in water specifically. And naturally, one water molecule in 550 million dissolve to form two separate ions, a hydrogen ion and a hydroxide ion, say. What that results in is what we call the pH scale, which is a measure of the concentration of hydrogen ions in a solution. And it ranges from 0 to 14 on the scale. I'll show you the scale in just a sec. pH of 7, that means it's neutral. There's the same amount of hydrogen ions and hydroxide ions in that solution. But if we get an imbalance in hydrogen ions, that's when we talk about acids and bases. So if there's more hydrogen ions, the pH is what we call acidic, and we measure it between the numbers of 0 to 7. And it's stronger the lower the number. pH above 7 up to 14, which is the highest number on the scale, we call those bases, and those have more hydroxide ions. Okay? And each number, each pH unit that you go up represents a factor of 10 times the change in concentration. Okay? So if you have a pH of 3, it's 1,000 times stronger than a pH of 6. Okay. And here's what the pH scale looks like. So it goes from 1 to 14, 7 in the middle. That's neutral. That's pure water because there's the same amount of hydrogen and hydroxide ions. So it's not at all what we might call caustic. It's not, those hydrogen ions aren't going to go crazy down here. Hydroxide ions go crazy up here, and they can cause damage to tissues. So we have strong acids at the bottom, weak acids and buffers around 4 to 6.9, right? And then the bases are at the top. And I don't know, everybody always talks about how acids are scary and ooh, battery acid and oh, acids. But remember, bases are just as caustic. They can be just as harmful as acids, just for different reasons. It's a different ion that can cause damage to tissues and cell membranes. Okay. So let's talk about acids really quickly. Strong acids are between 1 and 3, and these have a lot of hydrogen ions in them. Bases are strong between 11 and 14 because they have a lot of hydroxide ions, fewer hydrogen ions. This is stuff like bleach, ammonia. Soap is a weak alkaline base, and the ocean. Seawater is actually slightly basic. Okay? Your blood is almost neutral. It's like 7.3, I believe. Yeah. And then pure water, meaning there's no solvents in it, pure water is neutral. Let me go back to the acid ones. So when we have strong acids, again, it gets stronger as it goes down. So the lower numbers are stronger than the higher numbers. So stomach acid is the strongest acid in the human body. And then we get stuff like lemon juice and tomatoes around a 4. Normal rainfall is about a 6 because it's got some dissolved minerals in it that will change the pH a little bit. Okay. Whew. Yeah. And then we have buffers. So these are weak acids and weak bases, and they'll help balance the pH of other solutions. Okay? They neutralize things. Sorry, I'm scratchy today. Okay. And these buffers are actually produced naturally in the body to help maintain homeostasis, to get those hydrogen ions and those hydroxide ions to kind of mellow out and reform into water, essentially, is what neutralization does. All right, I think that's it for me today. I hope you are well. I hope you are happy and wearing your mask. And after you have finished taking notes on this, you should do the properties of water worksheet that is linked, I think, just below this on Canvas, the next assignment. And have a good week. Have a good weekend. Have a happy Thanksgiving. And be good, be kind, be safe, be smart, all of those things. Bye.